So now onto the main part of our presentation. Before I begin into the hardware and software, I just want to talk about why we chose this project in the first place. The thing is, salmon is an important part of our economy and our diet. In British Columbia, it's actually a keystone species, which means that many other animals depend on salmon existing in our rivers. It also brings nutrients to forests after spawning. If you remove salmon from British Columbia, it would be disastrous for the ecological system. There's also a market gap. We have systems that are too expensive. Expensive systems tend to be quite intrusive. For instance, many sonar systems require the building of a concrete funnel that is placed in the water so the fish that are swimming through it can actually be detected with the sonar. So we then decided to focus on putting our system in remote spawning streams. Small streams which can easily be captured with a camera which can only see 10 feet in front of it. In this case, the task we would be replacing is researchers walking up the stream, laboriously counting fish. We felt this would be valuable to researchers and conservation groups, and the DFO. So let's move on to the hardware overview of FishCenS. Let's start with the brains of it, the Raspberry Pi 4. That's what takes in all the inputs, that's what takes in all the peripherals, and then it outputs it to format that researchers can use. So in terms of peripherals, what we have is a Pi camera V3, a wide view camera. Then we have such things as the RTC module, the depth sensor, and the temperature sensor. We have an LED driver, which is on a PCB. And then that PCB is attached to a PoE hat, power over Ethernet, so that we can power and also connect to it externally via network. It's powered by a solar panel system, so it's got a charge controller, the panel itself, and then a 12-volt battery so that the solar panel can charge the battery and then the Pi can be run off that battery. The way we physically attach this whole thing so that it can be placed in a river is with a base frame, which has a capsule mount on it, and a Pi mount, light mount, etc., etc. So one problem that we ran into is that we had all these components that need to work together and have connections to the controller and also have a compact form factor. So what is something that we can do to bring a lot of this together? Well, one thing that we did was we built a custom PCB. We designed this ourselves, and the idea was that we could connect all of the components and also allow the peripherals to be connected in a compact form factor that could just sit on the Pi. We used KiCad to design this, and then we sent the design off to a factory and they returned it to us, and then we soldered the components and whatnot on there. This is the finished PCB. You can see here is the transistor, here is the RTC spot, and then here is the connection points for the temperature and the ultrasonic sensors and the LED. Another issue that we ran into is that all these need to fit inside a capsule. Furthermore, the capsule needs to be able to be angled and the LED needs to be able to be angled. This has to do with the fact that river beds or stream beds are not level. So we need to be able to adapt to that. So our solution was to design all these mounts and chases in SolidWorks and then print them with our Capstone 3D printer. This was a very iterative process. We had to go through several designs before we got something that was sturdy and what worked. Another thing that we ran into is the base frame. Capsule needs to mount on it. It needs to be able to hold the depth sensor at a reasonable height. And the LED also needs to be mounted to it. And furthermore, it must be stable enough to remain in place while in moving water and on an uneven stream bed. So this is something we went through a couple iterations with. Originally, this was designed with wood, but it wasn't stable enough. You could probably see right there that it's going to be quite tippy. But probably an even bigger problem is that wood floats, so you need weights to hold this down. If the stream bed is 1 foot high and you're placing the capsule in it, That's not a big deal. You can easily attach the weights to it. But what if you're placing it in water that's 4 feet or 5 feet high? Well, in that case, it's going to be very difficult to be able to attach a weight to it to hold it down. So we redesigned this to incorporate galvanized steel. We first drew this in SolidWorks how we wanted to come together, and then we put it together afterwards. It was much sturdier, heavier, and it was actually modular. So that leads us to the software component of this presentation. We want researchers to be able to, in a live sense, be able to look at what's happening. That means there needs to be real-time processing. We're not relying on video being post-processed after, which you have all day to do. We want it to be able to be looked at currently and see how many fish are currently in the stream. Fish monitoring and counting. The software must accurately detect and count fish in underwater video footage. The software should be able to track their movements to keep count. So what I mean by that is there's a lot of things that move in the water that aren't fish. Sticks, bubbles, and as you'll see later, reflections of the fish. We don't want to double count fish because of their reflections. We decided to use OpenCV for much of the computer vision tasks that were in this project. While machine learning and therefore TensorFlow took care of the identification of the fish, OpenCV took the identified fish and ran with it with tracking algorithms. And why that's important is if you have 50 frames, but one fish in those 50 frames, you can't count 50 fish. You have to count one fish. So you need some way of identifying from one frame to the next that that is the same fish. That's where tracking algorithms come in. Multi-threading and optimization. Because of the said tracking algorithm, we need to minimize the amount of time from one frame to the next. If there's too much time, then our tracking algorithm can't identify that that is the same fish. It's either too different in shape or color, or it's just too far in the next position to be able to continuously see, hey, this is the same fish. And Python integration. Our machine learning model was accessed via machine learning algorithms written in Python. That's the way TensorFlow wants you to write it, and therefore that's the way we did it. But our main program is written in C++, so we needed some way of being able to access with Python the machine learning algorithm, but with C++. We actually just used python.h or CPython library and integrated that into our program. So one problem area I wanted to talk about was our camera. The problem was the wide angle camera, which was new at the time, wasn't working with the current libraries that were out there. It didn't have any wide angle view support, and so what was happening was cutting off the left and the right side of the camera, which wholly defeated the purpose of why we got that camera in the first place. Furthermore, even though that camera came with autofocus capabilities, the library wasn't set up so that it could use it. So what we actually did is we downloaded libcamera's source code, and we found the areas that it was using to get the resolution and therefore get the shot, and we fixed that. So we changed the resolution that libcamera was trying to access the camera with, and we also found places where autofocus was disabled and enabled, and we just enabled them. It actually took a lot of work. Libcamera has a pretty large code base with a lot of people working on it. There's also quite a bit of things such as inheritance and many classes down the chain before you could really find where it's actually setting these things. So I'm not going to go through our code base too much here, but I just want to show that it's out there, and I encourage you to take a look through it if you are so inclined. The main two spots of interest are the area where we access the machine learning model with Python, and then the source code for the whole system. Our main.cpp is pretty light. It's really just giving us options for modes we want to access this program. But FishCenS.cpp, that's the main program. It's a huge file. I'm not going to go through it too much. But here is where you can see that we downloaded LiveCamera's source code and altered it. And in the tracking folder, this is actually where the main part of our program actually is. So FishML wrapper, this is what allows us to be able to connect to our Python script, which is accessing a machine learning model and detecting whether something's actually a fish. And in Fish Tracker, I'm just only going to the .h file right now, but this is what is taking care of the actual fish tracking. The machine learning identifies that as a fish, and the tracking algorithm tracks that area or that mass as it travels through the shot. And if we go to the sensor folder, you can see the temperature implementation, the temperature sensor, and the depth sensor implementation here.